All right, in this section, we're going to learn how to do these related rates problems. And all these problems, they're all word problems, and they're word problems in which they describe a scenario that's changing, right? So there's something changing over time. And they describe how some quantities are related to each other, like, say, area of a rectangle, how it's related to the length and width, or volume of a cylinder, how it's related to the height or something. So they describe how the quantities themselves are related. Then they tell us what rate one quantity is changing at, like how fast one quantity is changing. So they're telling us a derivative. And they want us to find how fast the other quantity is changing. So we want to find another derivative. Our general strategy can kind of be summarized here in this list. Identify the quantities we're talking about and any known rates. Also, I'm going to add to this and the rate we want to find. Sometimes it's helpful to make a sketch. If it is, go ahead and spend a couple minutes doing that. Determine the equation relating the quantities to each other. So sometimes it'll be just maybe a geometry formula. Sometimes a sketch will help us get that value. Sometimes they just describe in language kind of how they're related to each other, like a variation problem. And you'll see that a few different examples here as we work through these. Now, this part is really important. You determine the equation relating the quantities to each other. We want to solve a problem that's about their derivatives. So the way we get an equation about their derivatives is we differentiate that equation with respect to time. These are time rates of change. Then we should be in the position to solve the problem. So our first example, we have a spherical balloon. So imagine this balloon is a perfect sphere. It's being blown up such that its volume increases at the constant rate of 2 cubic feet per minute. We want to find the rate at which the radius is increasing when it's 3 feet. So this problem is about the volume of a sphere and how it's related to the radius. So right off, we could go, if we don't know this formula, we could go search it out, but the volume of a sphere is given by 4/3 pi r cubed. Now, I guess I've kind of skipped ahead, I guess, to step 3 in this list up here. The quantities that this problem is about is volume and radius. Now they tell us, I'm going to highlight this, the volume increases at the constant rate of 2 cubic feet per minute. That's a known derivative. We know that dv dt is equal to, it's increasing, so it's a positive 2, and it's constant, so dv dt is always equal to 2. We want to find the rate at which the radius is increasing when it is 3 feet. That's when the radius is 3 feet. Now, they're not telling us that the radius is always 3 feet. The radius is not constant here. This is describing a scenario that's changing over time. But we want the rate at which the radius is increasing, so we want dr dt when r is 3. It's really important to note that these quantities are changing because I can't plug in r equals 3 to this equation that we have. R is actually changing. So what we need to do first is differentiate with respect to time and get the equation that involves these derivatives here. So if we differentiate with respect to time, on the left side we get dv dt. On the right side, let's see, we'll bring down the factor of 4/3 pi, and then using the power rule here, we get 3r squared. Now, we are respecting time, so we have to use the chain rule, times dr dt. Notice right now, I have an equation that involves dv dt and dr dt. That's a good sign. And we know that dv dt is always equal to 2, so I'm going to go ahead and put that in. So 2 is equal to, do a little canceling here, those 3's cancel, 4 pi r squared times dr dt. Now I'm going to just solve this equation for dr dt. We could do a little reducing here. So we get dr dt is equal to 1 over 2 pi r squared. So we have dr dt expressed as a function of the radius r, and now we can evaluate it when r is equal to 3. So that's 1 over 18 pi. The units here, this is one reason why the dr dt notation instead of, v prime and r prime is desired here. When I use dr dt, that kind of just tells me what kind of units I need. Units of r over units of time. Units of radius are feet in this case. Units of time were in minutes. That I know it's minutes because those are the time units used in the rate of change of volume. So that means that my units for dr dt are in feet per minute. And in an applied problem like this, it probably makes sense to go ahead and approximate. So I get 0.0177 feet per minute. And you'll notice that while the volume is increasing at a constant rate, the rate of change of the radius is not constant. It depends on what the radius is. And that is sort of an interesting observation to make about this problem. All right, in this next problem, they describe the kinetic energy in joules of an object. They give us an equation. They say that this kinetic energy is 1/2 mv squared, where m is the mass in kilograms of the object, and its velocity is v. So then they tell us we have a 250 kilogram wrecking ball accelerating at 5 meters per second squared. How fast is the kinetic energy changing when the velocity is 30 meters per second? So in the beginning, we want to kind of just understand the quantities they're talking about a little bit, or at least the equation we should use. They tell us the equation, which makes it a little bit easier. 1/2 mv squared. There should be a derivative that we know, and there's should be a derivative that we want. So they tell us that this wrecking ball is accelerating at 5 meters per second squared. Acceleration is the rate of change of velocity, so we actually know that dv dt is equal to 5. We want to know how fast the kinetic energy is changing when v is equal to 30. So that's a rate of change of k. So we want dk dt when v is equal to 30. Now, initially, when we look at this equation, it kind of seems like we have 3 variables and not 2, but they tell us that the mass of the wrecking ball is 250 kilograms, and the mass of the wrecking ball isn't going to change as it's swinging, right? That's fixed. So we can plug that in first. This is a really important distinction. Quantities that are fixed and not changing, we can plug in those values if we know them right off. Any values that are changing over time, we can't plug in those values until after we take a derivative. So I'm going to plug in the mass. One half of 250 is 125. So now we have an equation just with k and v, and that's perfect for the description, for the problem that we're trying to solve. Now let's go ahead and differentiate with respect to time. We find that dk dt on the left is equal to, on the right side, when we differentiate with respect to t, we get, 250 v times dv dt. Now we know dv dt is equal to 5. So dk dt, 5 times 250 is 1250, so is 1250 v. And now we can evaluate dk dt when v is 30. We get 37,500. And the units here. Okay, so all of these problems have units, and I'm going to take, I'm going to figure out what my units are just by looking at units of the variable k over the units of the variable t. So kinetic energy, they told us, is in joules, and our time rate of change is in seconds because it'll inherit the time units used in the problem. So we get 37,500 joules per second. All right, one more here. This problem is a classic related rates problem. They describe a ladder slipping down along a vertical wall. The ladder is 10 feet long, and the top of it is slipping at the constant rate of 10 feet per second. So slipping down the wall. I'm going to just kind of start sketching this out. Let's say, this is the ground here, and here's my ladder. The ladder is 10 feet long, so that's fixed. I'm going to just label that in the figure. I'm also going to make what I think is a reasonable assumption that this building is erected straight, perpendicular to the ground, so we've got a nice right triangle here. Now, the ladder is fixed at 10, but it's slipping down from the top, which means the bottom is kind of kicking out down along the ground. So these distances here are going to be changing, but I'm just going to call the bottom distance, I'll label that as x, and the vertical distance, I'll label that as y. Let's see if we can identify what rate they've given us and what rate they want us to find. What's the derivative they've told us, and what derivative do we want? And maybe you think you know, maybe you want to pause the video and kind of write out what you think it is before I tell you what I think it is. So they tell us that it's slipping at the constant rate. The top is slipping down at the constant rate of 10 feet per second. So that's a rate of change of y. And if it's slipping down at 10 feet per second, that means y is actually decreasing. That length is decreasing. So we know that dy dt is negative 10. And we want to know how fast is a ladder moving along the ground. Like x is increasing. We could sort of conceptualize here. We know that x should be increasing, but at how many feet per second? So we want dx dt, and we want to know how fast is the bottom moving along the ground when the bottom is 6 feet from the wall. So that's when x is 6. All right, so we kind of have our nice figure here. What we don't have yet is an equation that relates the quantities x and y. But it's not hard to come up with one. Drawing the figure really helps here because we can see we've got a right triangle, and so we can use Pythagoras. So we get that x squared plus y squared is equal to 10 squared. Now, I might be interested in what's happening when x is 6, but x is changing over time, so I cannot plug in the value x equals 6 until after I take a derivative. Let's differentiate this equation with respect to time. When we do that, we get 2x dx dt plus 2y dy dt equals 0. right? 10 squared is a constant, so its derivative is 0. And we know that dy dt is negative 10. So I'm going to plug that in. Whoops. This will be a minus 20y, and that's still equal to 0. I want to find dx dt, so I'm going to do some algebra, solve this equation for dx dt. I'll throw the 20y on the other side. And divide both sides by 2x. So we have dx dt now. If we reduce, we get 10y over x. But you'll notice dx dt is expressed as a function of both x and y. So we need to know both x and y in order to evaluate it. Would they tell us that we're interested in what's happening when x is 6? And so we're just going to do a little side work. We're going to find y when x is equal to 6. And we can do that just using the original, Pythagoras here. So 6 squared plus y squared equals 10 squared. And we can subtract 100 minus 36 is 64. So y is equal to 8. We know it's positive 8. It's a distance. So we now know both x and y, and we can evaluate. Let's see, 2 goes into 6 3 times, goes into 8 4 times, so we get 40 over 3. So 40 thirds. The units are going to be units of x, that's a distance, in this case it's feet, over our time units, and that's seconds. So 40 thirds feet per second, or if you approximate, we get 13.3 feet per second.